Hi, this is Professor David Farina. In today's lecture, we're going to talk all about telescopes and specifically about radio telescopes. How are radio telescopes different than a normal telescope? Why do we use radio telescopes? These are all great questions. Let's get started. So, radio telescopes are actually not so dissimilar from a normal reflecting telescope. In fact, in many ways, they're identical. In a radio telescope, we have our incoming light rays, except for their radio waves now, which is a type of light. The light's coming in, and it hits the collecting area. The collecting area is simply a reflecting style telescope. It's a curved surface, and for a radio wave, it's acting like a mirror. And then that mirror, that surface, bounces the signal up to this little detector. And this detector is like a camera, except for it's just an antenna. It's a radio antenna like you'd have on your car, but much more sophisticated. Now, with this design, we are dealing with generally a prime focus style mounting. So prime focus, if you remember from our previous video on our designs, is when we have the detector at the very top of the telescope, at the focal point. This is important because it makes it for a very fast and efficient design. Now, when we're dealing with radio waves, these waves are significantly larger in terms of their wavelength than visible light is. They could be the size of mountains in some cases, and as a result, that means that they have a lower inherent resolution. In other words, when we use a telescope that's in the radio frequencies, we can't produce quite as clear of an image for an equally sized optical telescope. So we need to make radio telescopes absolutely enormous. Fortunately, they're a lot easier to work with than a visible light telescope is, and we can make some really big telescopes as a result. Now, if you recall, radio waves are part of the electromagnetic spectrum. And on the electromagnetic spectrum, they're the only other type of light other than visible which makes it all the way to the ground. The atmosphere of the Earth is going to absorb most of the electromagnetic spectrum. Radio, however, as this diagram shows, makes it all the way to the ground at these wavelengths, which you would associate with UHF and VHF. If you're watching this and remember back in the early days of television, over-the-air television through antenna, you might know a little bit about UHF and VHF. These bandwidths are starting to now be used by telephone providers for high-speed internet. There's also discussion for going into the microwave, if you've ever heard of 5G. But you'll notice that 5G is not going to have it's not going to easily be transported through the atmosphere because the atmosphere absorbs it very readily. FM and AM radio stations also are the radio stations you might tune into in your car. So those are the radio waves. Now, this is a very large dish, which is focusing our radio waves, and you'll notice that it is kind of see-through. It's a mesh, and it allows visible light to go straight through it. Yet with the radio waves, it sees it as a solid object. Once again, because of the wavelength of these are much larger. So once the light enters the telescope and is detected, it's then sent through an amplifier, which brings the signal up and the noise up too. So you need to then use a computer to process the information and determine what signal is and what's noise. And by noise, I mean kind of like the static you'd get on the radio or on a television. If you ever had one of the older televisions, the snow that you would see in your image itself. Now, radio waves are mapped in a similar way to what you might see when buying tickets for a baseball game, for example. So you have the highest priced seats right behind home plate, a little bit cheaper as we get farther out. even cheaper. And then finally, these purple ones are the cheapest seats in the house, the nosebleeds. So with a radio map, we color code it as well. So we have darker or more red areas here that or orangish colors that are going to be the strongest of these radio waves, and then we're going to go progressively cooler colors. The bluer and violet colors are going to indicate weaker radio waves, and then black indicates no radio waves whatsoever. So in this image, you can see we've combined both a visual image, a visible light picture of a galaxy, and with that, you cannot tell that there are these enormous radio lobes, these radio emissions that are sticking out the top and the bottom of this galaxy, which we now know is coming out of the black hole in the center of the galaxy, the supermassive black hole. So that's really neat. And by providing multiple different wavelengths of light, we're able to see much, much more. It's kind of like a doctor would use various different techniques to, for instance, an X-ray. To look into, see your bones, but they might use an MRI to see more of the musculature and the ligaments and tendons. So we use different types of light to see different things, and as a result, we can learn more. One of the benefits of radio astronomy also is that we can look straight through the daytime sky, so we can observe 24 hours a day, 7 days a week. Snow, rain, clouds, they don't interfere either, so you're constantly taking data, and as a result, radio astronomy in practice is a pretty good way to do astronomy. However, keep in mind there are radio places, or I should say places where radio waves are hard to deal with, because we have got civilizations, use of radios for various different things like cell phone towers. Microwaves can interfere with it, like the microwave you have in your house. So we need to be careful when we're building a radio telescope that we're not going to get so much interference that it's useless. Now, where are the largest of radio telescopes? So the United States, up until recently, has had two of the largest radio telescopes in the world. The first one in the mainland of the U.S. is the 100-meter Green Bank radio telescope. This is the largest moving dish of any telescope to this day. Second is the 300-meter radio telescope in Arecibo, Puerto Rico. This dish is stationary, and they move the receiver on the top back and forth with these cables in order to see a part of the dish. They don't ever use the entire dish in its entirety, and I'll show you that in the next slide. You may recognize this, by the way, from the movie GoldenEye with James Bond. So, as I said, the United States, up until recently, held the title for the largest telescope, but China has now passed us. The 500-meter aperture spherical telescope, or FAST, is a 500-meter radio telescope, and any use of this in comparison to the Arecibo, you can see the major difference in size of FAST versus Arecibo, and each of the partial disks, and this is what I was saying about with Arecibo, it only uses part of the disk. Each of the partial disks is equal in size, 300 meters, to Arecibo's mirror in its entirety. So Arecibo only uses a partial piece of its dish. This one uses an Arecibo-sized partial disk. That's impressive. Now, with radio astronomy, we can conduct a process called interferometry. This fancy word simply means that we can take the distance between telescopes and we can use that distance to create a virtual telescope. In other words, these telescopes are in what we consider an array. And so this telescope way out here and all of these telescopes are communicating together as one very large virtual telescope where we could basically draw an imaginary line in the diameter of this thing, and we can combine all of their resolving powers together. So this is a tremendous way to do astronomy. Now, it is important to consider when you're doing interferometry that you need to preserve the phase relationship between waves. In other words, we need to synchronize them. So just like in an optical telescope, we have a resolving power equation. For radio telescopes, this becomes an issue. So because the wavelengths are much bigger, much longer than visible light, our resolving power is less. So this is where interferometry steps back up again and allows radio telescopes to have very high resolutions by taking multiple telescopes and connecting them together to make a single image. Even larger arrays do exist and are being built. So we've got the very long baseline array and even the very long baseline interferometry. These two networks, we've got this one, this top one here. Each of those little dots is a telescope location, and we're communicating over the internet together, putting them all in phase, and then we are taking one image together and combining to produce our image. So this is a virtual telescope of this diameter, the most distant two components here and here. This is the very long baseline array. The second one includes telescopes from across the Earth, and this is the very long baseline interferometry experiment, a virtual telescope the size of the entire Earth. So when using these telescopes as an interferometer, we can actually match the optical resolution telescopes pretty closely. But this is very challenging to do interferometry for visible telescopes, but it is possible to do this. So interferometry can be done, like we talked about with Keck, like we talked about with the VLT, the Very Large Telescope in Chile, but it's so much easier to do when you've got the ability to pipe this information over the internet like you can with a radio telescope. With interferometry and visible light, you physically have to have the beam splitters in place, and you have to transfer the actual physical light beams from one telescope to the other and combine them together to produce the image. Much, much more difficult. Once again, I bring up the moon, a great location to do radio astronomy, especially the far side of the moon. It never faces the Earth, which means that we don't get all the radio emissions from all of our everyday activities, like our radio broadcasts, like television, like our satellites and internet. So the moon, and the far side of the moon specifically, could be a wonderfully large interferometer that could gather data for us without hardly any noise from the Earth. So thanks for watching today's lecture about telescopes and radio telescopes. I hope you liked this video. If you did, please like and subscribe. And if you'd like to get a notification every time I make a video, please click that bell at the bottom. Thanks, and have a great rest of your day.